Okay, so now we're ready. Let's take a look at what's happening. The limit as x approaches 2. Now, if you're working out a multiple choice question, ultimately, in terms of the AP exam, people aren't going to be scrutinizing your work, okay? Because it'll be multiple choice. You'll choose an answer. I'll be looking at your work, obviously, when you're doing multiple choice questions for me, but I won't be super duper picky about how you write things. However, if we're going to do a problem like this as part of a free response question, we have to write things perfectly in terms of mathematically accurate. So one of the things you notice I'm doing is I'm still taking the limit of a function. I'm changing the way the function looks, but I'm still taking the limit until I get to the end and substitute 2 in. So the next thing I would write, after I write the limit of this function, and I multiplied by that, which is legal because this is multiplying by 1, is going to be the limit of 9 minus the quantity x plus 7 over x minus 2 times 3 plus the root of x plus 7. All right. Yeah, no, maybe. Yes, so I foiled this guy and this guy, right? So 3 times 3 is 9. Conjugates, outside, inside, adds the 0, so I don't care about it. And then, so first minus last, the root of x plus 7 times the root of x plus 7 is x plus 7. But because it's behind that subtraction, I gotta make sure I group it. Okay. It's not the calculus that's hard, it's the algebra. The algebra will get you. The idea that we're going to ultimately plug a 2 into this, that's not a big deal. But to get it in a format so we can plug the 2 in to generate the limit, that's where all your algebra skills come in. Okay, so now I'm looking at the limit as x approaches 2 of what's ultimately going to be 2 minus x and x minus 2 and 3 plus this root. All right, how we doing? If you're like, crappy, I had 16 minus x, it's probably because you didn't distribute the negative. If you kind of just was like, hey, I know it's going to be x minus 2, it's not x minus 2 though. You were like, I'm just going to fake it. This times this equals x minus 2, magic. It doesn't equal x minus 2. But I can still solve the problem because it doesn't equal x minus 2, it's okay. It equals 2 minus x. So when I divide out, if I divide this factor and this factor, x minus 2 and 2 minus x are opposites. So what happens when you divide opposites? You get negative 1 instead of just 1. So it's the limit as x approaches 2 of negative 1 over 3 plus the square root of x plus 7. Final answer on this problem is negative 1/6. Okay. I'm going to say something kind of just a little teeny tiny mean, but well-intentioned. This might be a reality check for you. This is what AB is. Okay? This is not just like, oh, well, today, but it's good. No. It's this and this kind of stuff a lot. It's more this than easier stuff. if you want to learn some calculus, but you're like, this is way more than I want to do, then maybe you want to take applied calculus, in all honesty. Now, unfortunately, that will mean you'll have to change your schedule, because I'm the only one that teaches applied, and obviously I don't teach at 8th period because I teach you. Okay? So, and I'm not telling you need to do that. But I'm asking you to assess right now. I think between last class and this class, we started to kind of get a feeling about, here comes the rain. You know, this class is not going to be easy. It doesn't mean you can't do it, and it doesn't mean that I can't help you get better at some of these things. But this is more normal than not for this course. And if you've come through Honors Algebra 2 and Honors Pre-Calc, you're a little bit less feeling like you want to vomit looking at this because you're used to it. In regular Pre-Calc, it probably, not as much. Definitely not. And definitely not last year. Okay? So, just as something to think about. Before we get too far, not telling you to change your schedule, I'm just saying, think about how you feel and think about what you're going to have to do to try to be successful. This is a pretty standard question. And I will tell you, at multiplying with a conjugate and things, yeah, I'll do this in applied a little bit. I may or may not do this, but it's just the approach is a little different and the pressure is a little different because we're not really bound by the idea that there's a bar at the end that we have to meet. All right, 15. No conjugates. Conjugates aren't going to work. Conjugates are good for roots for these problems. So this definitely is not a conjugate problem. It's not a factoring problem. It's not an expanding problem. What else could I do to this to rewrite it? Go ahead. Okay. So how would you do that? Okay. So if I multiplied the entire top by an x and the bottom, thank you, you would have to do that to both. So I have to multiply my whole numerator by x, my whole denominator by x, so that I'm technically multiplying by 1, so nothing's really changing. Let's see what that looks like. So that's the limit as x approaches 1 of 1 minus x. Okay. When I take 1 over x times x, so this is a little bit of like rational function simplification, cleaning up a rational expression, a fraction inside of a fraction, as it were. So 1 over x times x is 1. 1 times x is x. Denominator, watch me again, not multiplying, just letting them sit. That's a pretty common theme when I do this. I'm going to want something to change, but usually the other piece, I'm changing it, but I'm going to leave the pieces just sitting. I'm not going to FOIL everything out. 2 conjugates, yes. I like to FOIL those because I know that's going to make a really pretty answer. The other 2 parts, I just leave them. 1 over x minus 1 times x, yeah, that makes that look a little different. Denominator stays the same. Just times an x. Opposites gives me -1. Value of the limit, -1. Let's see where we go. Hang on a second, guys. Yeah, you're all right. Hang on there. Okay, I thought that was the last one. Okay. So in three of the cases, we multiplied by a form of 1 to rewrite the original function expression. In 2 of the cases, it was a conjugate. In this case, it was just a single x that I used because of that 1 over x kind of gave me, that was kind of my focus, was like, maybe I can rewrite this part so I don't have a fraction. The expanding ones are usually the most obvious with the squaring. Okay. Once I do the algebra operation, though, the goal will be the same. Every time I do something, I'm going to hopefully get to a point where I see a common factor that comes out, because the common factor that I divide out is what is making the 0 over 0. If I can take away the common factor, that takes away the 0 over 0 scenario, and then I'm able to see the limit. Now, the homework that you had for today, or I think what was on your assignment sheet for today, I think this is what I was kind of talking about when I was talking about some of the problems, saying some of them you could do and some of them you might not be able to do. Let me pull this over here. Come here, Mr. Calendar. Why don't you want to move? Why do you hate me? Oh, I'll make you loose. There you go, because you're in the window. You're not just the calendar. Okay. So, in this set of problems, I think, some of the ones in 24 through 29, you needed what we talked about today. They were 0 over 0 problems that you needed a conjugate, or you needed expanding. A couple of these were graph reviews. 13 through 16 were, I think those were the vertical asymptote questions. I want to make sure you definitely go back in and take a look at 24 through 29 on page, somewhere between 66 and 68. That's where you're going to be able to practice this 0 over 0. I've got to do some algebra. Tuesday's lesson is not a lesson. Tuesday is our practice day. And one of the things that we're going to practice on that day is this 0 over 0, I need to fix it. Okay? So look at 24 through 29. If you skip some of those, or if you just kind of looked at my work for some of those, go back to them and look at them again. Try to look at them with fresh eyes and see if you can sort of figure out, okay, this is one of those 0 over 0s. This is the work I'm going to have to do. But know that we're going to review this some more and work on this some more on Tuesday. Okay? Now, the last part of this lesson 3 packet actually just kind of gives us the rules that tell us, hey, straight substitution works lots of times. As long as individual function pieces have limits that are defined, then I can take the limit of sums, of differences, of products, and quotients, and a number times a function. I can do a lot of limit calculations fairly easily. We kind of already used most of these rules as we were doing these problems, because every time I took something like this and ultimately then started to kind of just substitute a 2 in to this cleaned up version, I was using limit laws. if I take the limit of this quotient of the -1 over the expression, it's the same as the limit of the -1 over the limit of the expression denominator. And then the limit of the 3 is a 3, and the limit of the root of this is the square root of 9, which is also 3. So I don't want you to get upset and uptight with this whole sort of list of rules. Okay? We present them because they are what we're using informally to calculate limits. And every time we do a substitution problem, essentially we're working with one of these rules. Where you have to make sure you know them and that they work is when you have things that are a little less exact. Like, for example, let's say I give you, as we have here, information about two limits of the same function, two limits of two different functions as x approaches the same number, in this case b. So I'm telling you, okay, the limit of this one function as x approaches b is 7, and the limit of this other function, the g function, as x approaches b is -3. I don't actually need to see the f function and the g function explicitly to calculate limits using them. That's more of what these rules say, starting with D. If I know the information about two limits, and I want the limit of the sum of those two functions, the limit of the sum of the two functions is going to be the sum of the two limits. The limit of the difference of two functions is just going to be the difference of the two limits. It's like, and I'm going to totally air quote this because I'm not doing this, but it kind of feels a little bit distributive. You're like, oh, it's like you can just limit each piece. And that is exactly what you're doing. That's not a mathematical thing. We're not distributing a limit. We're not distributing the limit function, but that essentially is what happens by the definition of a function when we take the limit of a sum or difference of quotient or product. It breaks down into, I can look at each limit separately and then apply the operation. So A and B and C and D are pretty intuitive. If I hadn't shown you that whole list of rules and you just saw a question like A on a test, what would you guess the answer to be? 4, right? Because it is 4. It's very intuitive. It's intuitive. It works exactly the way you think it should work. You're like, I should be able to do each one and then add them. Yes. I want to do the limit of a sum. I can do two separate limits and then add them together. I want a limit of a difference. I can do the differences and then I can figure out the limits of each individual one and then do the difference. The limit of a product. Well, when your product is a constant, you can basically just kind of think about multiplying by the constant separately. Yeah, I don't know why I skipped down to C, but what would C be equal to? -15, right? What would B be equal to? -21, right? Because it would be essentially the limit as x approaches b of the f of x times the limit as x approaches b of g of x. It would be the 7 times the -3. Being able to use these rules to answer these questions is totally dependent on the fact that these were two limits as x did the same thing. If this had been limit as x approaches b and this one would have been a limit of x approaches c, then we can't do this. This has to match this given information for us to be able to essentially kind of break it apart. This is, well, the way I would write this one is it's 7 over negative 3, but I would write it as negative 7/3. I like the negative in the numerator. But what about E? You have a graph for F, and you have a graph for G to help you figure out the limit of F plus G of X. Now, that's just a slightly different notation. It's the same as saying I want the limit as X approaches 2 of F of X plus G of X. Just a different summation tool for two functions. Oops. I never thought up in that. Oops. A lot of oops in my life. What do you think, Johnny? Okay, so what do you, so ultimately you think the answer is 8? Okay. Because how did you get 8? Oh, okay. So no, I understand what you're thinking. Okay. We did have this information about the limits as X approached B up here. Okay. But the problem E doesn't have anything to do with those B limits. Okay. So problem E is strictly like F and G come from the graph. And this is not a product. And I know sometimes that's confusing. This is not the product of F plus G and X. This is the sum of F and G, and they're both functions of X. That's why I rewrote it down here. But thank you for answering. But I heard you say something that I think you understand. Once now we realize this doesn't have anything to do with the limit as B, if we're just using these graphs, Johnny, you want to give it another shot? Well, let's talk about the F function first. Here's the F function. The limit as X approaches 2 on this F function is equal to what? Is equal to 1, correct. So that limit, the F limit, is 1. What about the G limit? Is 3. This is why I heard you say this, and so I thought you were, oh, but you were doing that to before. Okay, I already got that. Okay. Okay, that's why I was thinking you were on the right track before, because you were doing 7 plus negative, and I was like, well, he said something about 7. Yeah, the final answer here is 4. The final answer is 4. All right. Yes, sir. Absolutely, yes. And you actually can just grab the pass and go. Yeah. Do not have to, but thank you for being polite. I know it's hard to get up when I'm talking, but if you absolutely, if you need to use the restroom and I'm talking, that's something to just get up, grab the pass, go. As long as the passes are there, you're welcome to go. Okay. All right. That lesson is a lot. That's like a whole lot of stuff in there. Okay. It's going to take time for you to think through it. definitely need to be working on it. We're going to continue to work on, I know you're thinking, is she done? No, we're going to do a little bit of 4 right now. I know, we're so tired, but we're going to do a little 4 right now. Let me just take you a little bit into 4. We can start. See where we get. Okay, I know we're not going to finish it, and we'll come up with a plan. I'm not worried. But let's take it into 4. Okay. We're going to do one, we'll see. Okay. Okay. So continuity. Totally change it. Not really, but an application of limits. Continuity. To be continuous at x equals c, for f of x to be continuous at c, we need f of c to exist. This is the same stuff we wrote down on day 1, right? We need f of c to exist. We need the limit as x approaches c from the left for f of x to equal the limit as x approaches c from the right of f of x. Which means that the limit as x approaches c of f of x exists. Okay. That second branch is the tough one because sometimes you got to do a lot of little talking to get that. It's like, I need to show I can get the limit. To get the limit, I need to talk about the left and the right. If I can get the left and the right limits to match, then I've got myself the limit. I've got a limit at c, I've got f of c, and what has to be true about those two things? When I get f of c and I get the limit as x approaches c, they have to be the same. Okay. F of c equals the limit as x approaches c. Now, the reason we write it in this like 3-step form, even though like the bottom line is really the important statement you have to make. You've got to say some things to get to step 3. By saying I can get f of c, here's f of c. F of c is 10. And then showing that my limits as I approach c from the left and right also work and come out to be 10. I've therefore shown I've got f of c and the limit as x approaches c to match. And that has created continuity. And you're saying, well, what's different in this lesson? We already talked about this. You're right. We talked about it conceptually. We talked about what we would have to see. We talked about a lot of discontinuity. Now we're going to talk about being really, really particular about proving continuity by showing the evidence through these steps. This is a communication skill. This is a free response skill. This is not as much about, or it's partially about the concept of continuity, but it's also about communicating about continuity. Okay. So let me show you, we don't need all these problems. Let me show you a good example. For example, problem 3, where I am going to prove and or disprove the continuity of this function when c equals 0, or I guess at c equals 0. So I'm going to show that f of x is either continuous or discontinuous at c equals 0. Now, there's lots of ways to make an argument about something. Our goal is to be able to make that argument as correctly as possible and as succinctly as possible. We don't want a lot of blah, 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 blah. We want to say everything we need to say and not one word more. And I'm going to write things in symbols instead of words because symbols are much more specific. Words that are bad to use are it, the function, the value, because they are all vague. So I'm not going to say, if I'm going to write a good communication proof, I'm not going to say, well, it's continuous because it's equal. What did you just say? I don't know what you're talking about. It's continuous because it's equal? Who's it? That's that big scary clown, right? We don't want any part of him. What's his name? Pennywise? No Pennywise questions, right? No it. And it's equal. What's equal? How do you, and if even if you are talking about two things that are equal, show me that they're equal. So, long story short, I'm going to give you a script, and my advice to you is to work with that script. Okay? I'm scripting it a certain way because it's the best way to be very clear and accurate. It doesn't mean it's the only way to say it. And I know some of you will try to go off script with me. And I'm not going to have a problem with you going off script. I don't mind that. You can, as long as you explain it clearly, then I'm fine. But the problem becomes when you write something and I read it and I say, I'm not sure what this means, I can't give you credit for it. I can't give you credit for something that I'm pretty sure I know that you know the answer. That's not how this works. I cannot do that. I cannot use the fact that I know you and I know that you understand continuity to take what you've written and read into it. All I can do is grade what you've written. And if you write, it's continuous because it's equal, that's going to be worth a big old donut 0. It's continuous because it's equal is not going to get you anything. In fact, you are never going to get any points for continuity if you don't talk about limits. So here we go. I'm going to start down the path of seeing if it's continuous. Either I'm going to get through the steps and at the end I'm going to go, yay, I'm continuous. Or I'm going to start down the steps and I'm going to run into something that's not true and then I can say, discontinuous, I'm done. So if I want to show I'm continuous or discontinuous at c equals 0, the first thing I should talk about is f of 0. If I can't get an answer for f of 0, if there's not an answer for f of 0, this problem's over. All right. Now, in this piecewise function, the part when x is equal to 0 is defined by the e function. So f of 0 in this function is equal to e to the 0. And you, my lovelies, can tell me that e to the 0 is equivalent to 1. All right. Because anything to the 0 power is 1 except for 0. And that could actually be a lot of different things. Okay. If I can't complete that step mathematically, if I don't have a value for f of 0, the problem's over. It's discontinuous. If I can't get a function value, it's discontinuous. Next thing I'm going to do. This is where, if you get to this step, this is where you're like, okay, now I'm going to be doing a lot of work. I'm going to do the limit as x approaches 0 from the right of this function. I decide to start from the right. That's just my preference. You can start with the left one if you want, whichever works better for you. I gotta do both of them. So if you want to write both of them down, you can. Okay. Now, lo and behold, 0 is exactly where this function changes. No surprise there that that's what we're interested in talking about. That's what's interesting. This function is not that interesting at x equals 5 because at x equals 5, it's over on the e part and we're good. At x equals -2, it's over on the x squared part and it's all good. At right around 0, though, is where I've got a change. So when I take the limit as x approaches 0 from the right, which of the definitions of this function is the right side definition, the x squared or the e to the x? Yeah, it's the e to the x. Because this is x is greater than or equal to 0. So that's the right side. So I need to show everybody that's looking at my paper that I know that means I'm doing this. Which you're going to say, well, that's the same as it's the same as f of 0. Yeah, but you still have to say it. It's where x equals 0. It's for x greater than or equal to 0, so it's the function value, and it's the right side limit. The left side limit is squaring the function. This is e to the x. This is x squared. Okay. Is this function continuous at 0? A couple people said no. A couple people were like, I don't have any idea. Well, let's see. F of 0 exists. Check. Left and right limits equal to each other. Not a check. Right. I can stop here with my steps. I can go to the answer now. I can say, therefore, f of x is not continuous or discontinuous, whichever one you want to use. Continuous at x equals 0. And then I'm going to tell them how I know that. Now, there's a couple different ways to say this. This is my favorite one. This is the easiest one to say it. If your limit from the left and your limit from the right don't match, then your overall limit doesn't exist, and you can't have continuity. However, you can't make a claim like this without the evidence. You can't write down and say, I know there's no limit because I know its function's not continuous at 0 because I know the limit at 0 doesn't exist. And I'll say, prove that you know that. How do you know it doesn't exist? That's what this is. You can't just tell me you know. Like, I know this is what I need and I've got it. Show me that you've got it. This has to be explicit. This is work. This is writing. This is not the most fun thing to do. And I know some of you are not going to want to do this. And you're going to try to figure out a way where you don't have to write as much. I'll work with you, but be careful. Because as soon as you start trying to tell me it or the limit, it's so much better to be very specific. It's the limit of f of x. as x approaches 0 from the right. Not the limit of the function. Which limit? Which function? That is how we start structuring a continuity proof. Okay. You will see later in this handout, we are not just writing about continuity, we are using and saying, if I tell you it's continuous, find a missing value. Okay? So some more continuity work is still to come. We are going to review and work on, we might throw a little bit of continuity in on Tuesday, we'll see. This may shift our schedule back a day. I'm actually okay with that. I kind of felt like that was going to happen going into day 3. Okay, so what you should do to make sure you're kind of on top of things is the homework assignments from the page 76 and 66, the big chunk of homework assignment from day 3. Work through all of that. And if you want to start looking at day 4, you can. If you want to try practicing what we did today, problem number 9 would be a good first one to do. Okay, let's listen up. Okay, yeah.
The extracurricular activities, team practices, or recreational programs taking place today. Please get on your attendance schedule. Additionally, Class 34 is going to be late. Please wait until